All right, so we're going to be going over chapter 2.5 here in these notes. We're going to be talking about solving right triangles and also how to apply these into solving some real world problems. So first piece here, when we say solving a right triangle, what we mean is finding any of the missing side lengths and any of the missing measurements of its angles. So there's a lot of different things that a lot of different initial setups we could be looking at in a given problem. So here in this triangle, we know two of the sides. We could find the third in a few different ways. So in order to solve a right triangle, we need to know at least three things. So first, it's got to be a right triangle, at least for what we're doing right now. We need to know at least one side length. If we don't know any of the sides, then we're not going to be able to solve this at all. And then another piece of information. Doesn't matter if it's another side or an angle. As long as we have one side and then something else, we can go ahead and start solving. Quick reminder here, regular trig functions, that's what we've been using kind of previously. What I mean by regular is just your standard trig function where it takes in an angle and it gives us out a ratio of sides. So, right, sine takes in an angle measurement and then gives us the ratio of the opposite over hypotenuse. To solve for certain parts of our triangles, the angles in particular, are going to need to be using the inverse trig functions. Remember that an inverse switches an input and an output. So instead of taking in an angle and giving us out a ratio, they're going to take in the ratio and give us out the angle. So that's going to be useful if we know this ratio, we'll be able to use the inverse sine, for instance, to find the angle. Or depending on which ratio we might know, we'll choose the appropriate trig functions. It follows the same SOHCAHTOA mnemonic. Now, technically, we could also use cosecant and secant and cotangent as well, but for the most part, we're just going to use the regular sine, cosine, and tangent. All right, so let's go ahead and use some inverse trig functions to solve for this angle in this problem. And that's what we use the inverse trig functions for. They allow us to solve for angles. So anytime we're solving for an angle, that's when we're going to be using the inverse trig functions. So it's very similar to what we do before. We pick our angle of interest, which in this case, or in these cases, is the angle that we're solving for. So in this case, theta or angle A. And then we mark up our triangle accordingly. So across from this angle is the opposite side. The leg next to it is our adjacent, and then the hypotenuse is obviously across from the right angle. So there are our sides. And then from there, we need to pick the appropriate trig function to use. When we're solving for an angle, we need to know two sides to actually create that ratio. So we know the opposite and we know the adjacent. So opposite and adjacent, that goes with tangent. So remember, tangent of the angle equals opposite over adjacent. But we're not using the regular trig functions. We're going to be using the inverse trig function. So we're going to be using inverse tangent. So inverse tangent of opposite over adjacent is going to equal our angle. Notice again how the inverse trig function takes the input and output and switches them. That's what we mean by an inverse function in general, but the same thing applies to these trig functions that are inverses. So let's go ahead and set up this equation really quickly. Tangent inverse of the opposite, which is 4, divided by the adjacent, which is 13. That is going to equal our angle. And now we just need to use a calculator. In these cases, a lot of times you either have to hit shift or second or something. And the inverse buttons tend to be right above the regular trig functions here. So here on my calculator, we have sine, cosine, tangent. And then right above them in orange is sine inverse, cosine inverse, and tangent inverse. So I have to hit shift and then tangent to get this. And then I calculate my angle measurement. My calculator is in degrees, so this is the degree measurement of that angle, 17.1 degrees. I'm going to round to 1 decimal place. Obviously, we can be sort of as accurate as we want in these problems. This is an approximation. Technically, I've rounded it to 1 decimal place, but we're going to be good with that. Once we have this other angle, it would be pretty easy for us to figure out angle B here if we wanted to. Right, B is actually complementary to the one we just solved for, because these have to add together to be 90 degrees so that our triangle sum theorem would hold. So I could just take 90 minus 17.1 and figure out that angle B here So measure of angle B would be 72.9 approximately. Again, once we know two of the, right, we know now two angles. We know this angle and this angle. It's easy to find the third. That's really the only point I'm making here. There we go. Let's move forward. All right, so let's go ahead and quickly solve these problems. Go ahead and pause the video if you want to try it on your own first. All right, so our angle of interest, we're looking for these question mark angles. So we're going to be solving for this one. We need to mark our triangle. So we have opposite, hypotenuse, adjacent. In this case, the two sides we do know that will help us solve for this angle are opposite and hypotenuse. So that tells us to use sine. So we have sine, I'm going to call this x to make it easier. So sine inverse of opposite over hypotenuse, which is 12 over 24. That is going to equal x. It's going to equal our unknown angle measurement. We could simplify this fraction if we want to and do it that way, but it doesn't matter. I'm just going to do sine inverse of 12 over 24. I'll show that here. We might have been able to figure this one out if we remembered some information from our unit circle. Because remember, 30 degrees, which is the answer we get here, is a unit circle angle, right? We might have remembered that at 30 degrees, the sine value, the y coordinate, is a half. So I think we would have expected that if we're taking the sine inverse of what is equal to 1/2, we're going to get 30 degrees. The x coordinate here would be √3 over 2. But for us, since we're doing sine, 1/2, sine inverse of a half, 30 degrees, that's kind of how these things are connected. Running through that quickly, what you really just need to know is how to solve for it using trig. All right, let's go ahead and solve for the next one here. We're going to use, let's see, what do we have? We have our angle, we have the hypotenuse, and we have the adjacent. This one over here is the opposite. So adjacent and hypotenuse tell us to use cosine. So we will use cosine inverse since we're solving for an angle. So cosine inverse of adjacent over hypotenuse is equal to, I'll call this one theta, is equal to theta. So I'm going to use my cosine inverse. Again, I could simplify this fraction, 6 over 8, but I don't need to. So 6 over 8. And I got 41.4 degrees. Showing that really quick, 41.4. So again, these are approximations. We are rounding them to 1 decimal place. Depending on the problem, you may want to round to more decimal places, but we are wanting approximations in these cases. We're not really looking to find exact values like we may have done in other problems. All right, let's go ahead and move forward. So when we're solving a right triangle, there are a few tools that we already know. Obviously, the Pythagorean theorem. If we know two sides of a right triangle, we can always find the third using the Pythagorean theorem. Complementary angles. So anytime we have a right triangle, and that's a terrible right triangle. Let me fix that. Anytime we have a right triangle, the non-right angles, the acute angles, are always going to be complementary, right? That's because we have a 90-degree angle, 90-degree angle here. That means that these two angles have to also add up to be 90, because 90 plus 90 is 180. And if we know we have one 90-degree angle, then these two angles, x and y, have to actually add together to be the other 90 degrees, because the triangle sum theorem tells us that all angles in a triangle add up to 180. So you can always make use of that. If we know one of these acute angles, the other one's just going to be complementary to it. So we can kind of quickly find that. And then these are the two big ones for this section, is using our regular trig functions to find side lengths, so sine, cosine, and tangent, and using our inverse trig functions to find the angles, so sine inverse, cosine inverse, tangent inverse. This is where the whole SOHCAHTOA thing is definitely something we want to have memorize and know which two sides go with the given trig function. And they don't change whether it's inverse or regular, right? If I'm using inverse to solve for an angle, And I know the opposite and adjacent, I'm still going to use tangent. Still applies for the inverse functions. All right, let's go ahead and keep moving forward. Right, well, let's go ahead and solve for this right triangle. There are a few initial steps we could take. Doesn't really matter. Since this is the angle that's given to me, I'm going to go ahead and start with that one and label my triangle. This is the opposite, the adjacent, and the hypotenuse for that angle, right? I can easily solve for angle B here. It's going to be complementary to A, so this one would be 39 degrees, because when I add those together, I do get 90 degrees. So angle B is pretty easy to find if I wanted to. That does lead me to another option here. I could use angle B as my angle of interest, and that would change this labeling around a little bit, but it also may make some sides just slightly easier to solve for, but it doesn't matter. I'm just going to use 51. All right, so from there, I need to choose whether I'm solving for this side over here, which is my adjacent side, or this side over here, which is my hypotenuse. Those are the only two things that I'm missing right now. Let's just say we solve for the hypotenuse. So the side that I know is the opposite side. Opposite and the hypotenuse tell us to use sine. So sine of 51 degrees is equal to opposite over hypotenuse. And I can go ahead and solve this really quickly. Multiply by h on both sides. I'm going to get h times sine of 51 equals 9, and then I need to divide both sides by the sine of 51 degrees. I want to keep this sort of exact until I reach the end here, and now perform this calculation to figure out what h is equal to. Again, rounding, I'm going to just go to one decimal place, but it totally depends on what the problem asks us to do. 9 divided by sine 51. And rounding this, I got 11.58083. I'm going to get 11.6, approximately 11.6. I guess we are dealing with inches in this problem, so inches. And at this point, we sort of reached a bit of another choice point for us. We now know two of the sides, and we could use the Pythagorean theorem to solve for the third side. We know two sides, so we can always use that to find the third. That's a totally fine option. We could also use trig. We can use trig to solve for this adjacent side. It doesn't really matter. I'm going to continue to use trigonometry this time, but it doesn't really matter. So I want to solve for the adjacent. I do know the opposite. I'm going to always go back to what was given to me rather than what I solved for. There's a few reasons for that. If I made a mistake here and then I use this measurement, then I know I'm going to be wrong, right? If this is wrong, then if I use a wrong answer moving forward, I'm going to be wrong, right? So I don't want to use that one for that reason, one. And two, this is rounded, whereas this is exact. So my answer is going to be more precise using this exact value that I was given rather than this rounded value, which I solved for. Very small things, but could make a very slight difference in our answer. Well, if I use a wrong answer moving forward, obviously that's no good, but the rounding is just a very small thing. All right, so opposite, adjacent, I'm going to be using tangent. So tangent of 51 degrees equals the opposite over the adjacent. Again, it's going to solve just like this. I'm basically going to get that the adjacent equals 9 over tan 51. And do that, 9 divided by tan 51. I get 7.288, and I'll just show it here. So 7.3 inches. Do be mindful of the units. Include units if they're given to you. If they're not, then it doesn't matter. But if units are given, make sure to include those with your answers. So now we've solved for the two missing sides and the one missing angle. We know everything about this right triangle. I'm going to go ahead and clear and move forward. All right, here's another one. A little bit of a different starting information. In this case, we know two sides. We're missing all of the angles other than the right angle, of course. So we can't do this the same exact way we did the last one. We'll have to go a little different. We have choices, though. we could first solve for this angle, this one missing angle, or I guess this one too, it doesn't matter. We have two sides of a right triangle. We could find the third using the Pythagorean theorem, or actually, in this case, this is a special Pythagorean triple. If you notice that, this is 4 is one of my legs, 5 is my hypotenuse. This is a 3, 4, 5 right triangle. We would get the same answer using the Pythagorean theorem, but if you notice this is a 3, 4, 5 triangle, it could save you a little bit. Again, let's just pretend we call this x. We could solve for this as well. X squared plus 4 squared equals 5 squared. X squared plus 16 equals 5 squared. Oh, sorry, that's 25. Let's just go and go that way. That is x squared, subtracting 16 from both sides equals 9. Taking the square root, we get x is 3, right? So same thing, but if we notice this, that would be useful there. All right, now we need to find the angles. So the angles, we're going to need to use our inverse trig functions. I'm going to go ahead and find this one. I can use any of these sides, right? Because this is actually an exact value. So I could even use that one if I really wanted to, but I'm going to use the ones that were given. So adjacent and hypotenuse. So that tells me to use cosine inverse of adjacent over hypotenuse. That is going to equal our angle theta there. And then I go to my calculator. Cosine inverse of 4 over 5. So I'm getting 36.9 degrees when I round that. 36.9. Write that down. And then to find A, I could use trig again, or I could just use the complementary relationship. I'm going to keep it easy. I'm going to use the complementary relationship. So 90 minus 36.9, 53.1. So this is a measure of angle A is 53.1 degrees. Again, I could have used trig for that, but a little bit easier here just to do a simple subtraction and use that complementary relationship. All right. And here's one more for you to go ahead and try to solve this problem. So pause it and give it a shot here. All right, I'm going to go ahead and start going through it now. Again, pause it if you'd like to try it on your own. There are a few things going on here. You could notice that this triangle is actually isosceles. And we know the base angles of an isosceles triangle are congruent. So these angles are actually congruent, making this actually a 45, 45, 90 triangle. So totally valid. You could do it that way. I'm not going to do that. Again, you could use your information. The answers are going to be 45 degrees, 45 degrees, 3 root 2. I'm not going to do it that way because I want to do it a different way. I want to show the trig way to do this. But you could do all that and it would be absolutely valid. So here, I know two sides of my right triangle. I'm going to go ahead and use the Pythagorean theorem to find my hypotenuse here. So 3 squared plus 3 squared equals c squared. That's 9 plus 9. And then taking the square root of both of these sides, the square root of 18 is not an exact value, so exact integer value. So I'm going to be breaking this down. 18 is 9 times 2. So square root of 9 is 3. We get 3 root 2 for our hypotenuse. Again, exactly what I said before if we used our 45, 45, 90 triangle to do this. And now I want to go ahead and use some trigonometry to solve for this angle. So I'm solving for an angle. I'm going to be using inverse trig. The two sides that I was given are the opposite and the adjacent. I could use the hypotenuse if I wanted to, because this is an exact value the way that I wrote it, but I'm going to leave it there. Let's see. So that gives us tangent inverse of 3 over 3, which is 1, but I'm going to do it as 3 over 3. Equals our angle. So shift tangent 3 over 3. 45 degrees. Exactly 45 degrees. That's interesting that the tangent inverse was 45. If we remember some information about our unit circle, we would remember that at 45 degrees, so at the 45 degree angle, so I just kind of quickly sketch that out here. The 45-degree angle, that's where sine and cosine are actually the same. They're both √2/2, right? The coordinates for that are square root of 2 over 2, comma, square root of 2 over 2. So the sine and cosine values here are the same. And tangent is the ratio of these values. Well, when you divide something by itself, you get 1. So when we divided this here and we got 1, we should know that if we do the tangent inverse of 1, the place where tangent is equal to 1 is right here at 45 degrees. Again, that's some advanced unit circle knowledge, but I just want to show the connection to that as we go through. So this angle is 45 degrees. That means that this angle would also be 45 degrees using our complementary relationship, and we've gone ahead and solved for everything. I guess I should mention we could have gotten a decimal version of that if we wanted to. There's no reason we can't, considering most of the time we were using decimal values. So this is approximately 4.2 if we were going that way. All right, so I'm going to go ahead and end this part right here. We'll talk about some of the application problems in the second part, and see you guys there.